This is the second video of the series Physics Made Easy for 10th graders. Dig deep into the concept. In the first video we introduced the topic of refraction of light. In this video we continue with refraction and define the various angles and study the laws of refraction using geometrical optics, ray tracing, and definition of angles. Let a ray from source S strike the interface of the two media at point O. Normal to the surface at the point O is ON. The incident ray SO makes angle I with the normal. This angle is called the angle of incidence. It is observed that part of the incident ray along SO is reflected along O. This partially reflected ray follows the normal laws of reflection, that is, the angle of reflection angle. NOA is equal to the angle of incidence. The intensity of the reflected light will depend on the smoothness of the surface and also on the angle of incidence. This is a normal observation. We see our reflection in a puddle of water or a shop window. On entering the denser medium like water or glass from a rarer medium like vacuum or air, the ray does not continue along the original direction but bends towards the normal. This phenomenon is called the refraction of light. The refracted ray OT makes an angle R with the normal OM, to the surface. This angle is called the angle of refraction. In absence of the change in the medium, the ray would have traveled along OP. The ray inside the denser medium is deviated by angle POT from the original direction. This angle is called the angle of deviation, denoted by delta. Snell's laws of refraction. Greek physicist Claudius Ptolemy in 140 AD measured and tabulated the angles of incidence and refraction through water. However, the reason why refraction occurs was not known at that time. Ibn Sahl, an Arabian mathematician in 984 AD, wrote a treatise on burning mirrors and lenses. His work, which explained how light is bent by curved lenses and mirrors, is credited with the discovery of the refraction phenomenon of light. The Dutch mathematician Willebrord Snell in 1621 AD independently formulated the laws of refraction that explain the measurements of the incident and refracted angles. Snell's laws of refraction are the result of a careful experimental study of the behavior of the incident and refracted rays. However, it is just a mathematical expression. No proof was known at that time. The proof had to wait till the early 1860s when James Clerk Maxwell showed through his equations that fluctuations of electric and magnetic fields travel in vacuum with a constant speed c and that light is an electromagnetic wave. Electromagnetic waves cover a wide range of spectrum from long radio waves to short gamma rays. The light rays fall in a small window of this spectrum. The first law, the incident ray, the refracted ray, and the normal to the surface lie in the same plane. In Figure 4, which is a simplified version of Figure 3, the incident ray SO, the refracted ray OT, and the normal ON, extended to M, are coplanar. Snell's second law states that the ratio of the sine of the angle of incidence and the angle of refraction is a constant designated as mu. The superscript medium 1 and the subscript medium 2 indicate that the light is traveling from medium 1 to medium 2. If the first medium is vacuum, then we drop the superscript and the subscript and write sin I by sin R equal to mu, equation 6, where mu is called the refractive index of the medium. The refractive index of the medium depends on the wavelength or color of light. If the wavelength of the measured value is not specified, it is taken to be the yellow radiation of sodium with an average wavelength of 589.3 nanometers. The refractive indices of selected materials are as follows. The refractive index of vacuum is 1 by definition. The refractive index of air at STP, that is, at standard temperature and pressure, is 1.003, that of water 1.333, and that of normal glass 1.52. The refractive index of polycarbonate used in spectacles is 1.60. The high value of mu for this material helps in making thinner spectacles. As the refractive index of air at STP is close to that of vacuum, the refractive index of any medium relative to air is approximated by the value relative to vacuum. Snell's laws of refraction are the result of a careful experimental study of the behavior of the incident and refracted rays. It is interesting to note that the two ratios representing the refractive index, one derived from the angles given by equation 6 here, and another from speeds discussed in part 1 of this series given by equation 1, are indeed equivalent. For a proof using geometrical optics, please refer to section 5 of my blog Physics Made Easy for 10th graders. Dig deep into the concepts, part 1. The link to this post is given in the description box. If you liked the video, please consider subscribing.